It is the 1st of October. Holy cow. Where has this year gone? The first one, nobody fell into the trap. Everybody got, okay, the average velocity for the trip is 0 because you end up back in your driveway. The average speed for the trip, the only confusion for some folks on number 1 was the total distance traveled. And the total distance traveled was 160 kilometers. It says in the problem, after traveling 160 kilometers, you return to your parking spot. So that is your total distance. That's not half your total distance. It's not 160 out and back. Final answer for that with sig figs was 34 kilometers per hour or 9.6 meters per second. If that's the only thing you messed up, that's easy. That's an easy fix. Just, more careful reading. Number 2, it takes you 5.14 seconds to grind to a stop. I don't think anybody missed that one. It was VF equals VI plus A delta T, and of course we're looking for delta T. So rearranging, you get VF minus VI divided by A gives you your delta T. Again, and I'm saying this for a reason on this one, and most of you did really well on the front page, list those variables. Seriously, closely look at what's given in the problem. Do not introduce things that are not there. Okay. So number 3, again, people did really well on this. Here you had VI, VF, delta X, and you were looking for A. So you can use VF squared equals VI squared plus 2A delta X. And of course we're solving for A, so we get VF squared minus VI squared over 2 delta X. Final answer with sig figs was negative 7.82 meters per second squared was your acceleration. And you do have to have that that's negative because your velocity was given as a positive and you're going from a velocity to a 0 velocity, so that acceleration has to be negative. I think just a few people missed that negative, but that happens if you flip your VF and VI, if you claim that you're starting from rest and coming up to speed. Okay, you're sledding, you took a running start, we're given, so we have an unknown VI, we have a VF, we have a delta X, and we have a rate of acceleration. So we need to use VF squared equals VI squared plus 2A delta X, and we're solving for VI squared. So VF squared minus 2A delta X, square root thereof, gives us VI. So a few people had some problems with rearrangement on this one, but not many. This one was pretty good. Final answer was sig figs, 4.48 meters per second was your initial velocity. So you did a pretty good little run. I think the people who did have problems with that one, the problems were algebra. I think it was misrearrangement. And like I said, we're just starting into our sort of dance with algebra in physics. I have had students say, like, this course made my algebra stronger than anything else because we do so much algebra. We do massive rearrangements. So, okay, are you ready for the last one? Any questions on that one? Algebra tutorial, so I can hit pause. So starting with reverse order of operations. So VF squared equals, let me give myself some more space here. Cut. VF squared equals VI squared plus 2A delta X. Well, if we subtract 2A delta X from each side, minus 2A delta X, whoops. Let me get that back. Copy, paste. So if we subtract it from both sides, on this side it cancels out. So now we've got VF squared minus 2A delta X equals VI squared. Does that make sense? And then you're just taking the square root of both sides. So then it's just a matter of that. And we can pop this whole expression in. Yeah?
I was trying to get the initial velocity directly out of it, and I just couldn't.
No, you can't. You have to.
No way to
You have to rearrange and solve. And I'm still seeing a few folks, and this kind of goes more to the general problem solving thing. You have to put down your base equation. You have to rearrange it for your desired variable before you plug in numbers. And over however many years of teaching, I think you guys are my 5th or 6th crop of physics kids, I have heard repeatedly, and I have vetted this statement with the math department. No, that's how we do it in math. And every time I say that to anybody in math, they go, no, they don't! So you got to rearrange before you plug in numbers. You have to do that because we're going to keep doing substitutions, which is what we're getting to in the next problem. Okay, so number 5, we have 2 mine cars. And they are both heading down a 272-meter shaft. Now, there are some things that we do tend to gloss over in physics problems, and some of you are getting hung up on the logic of the problem. You know, but one can't go any faster than the other, ever! So we'll run the numbers on that after we finish this. We have car 1, we have car 2, and different things are true for these 2 cars. So for car 1, what we are told, and we're already in the realm of fantasy, because we're told that car 1 is immediately at maximum velocity. Presto, there's no acceleration. It goes from 0 instantaneously to top speed. We know that's not physically possible. So we're already in the realm of fantasy here. So for car 1, what we know is that it says that the velocity is uniform. So it's got a single velocity. We could call that its average velocity. And we know that for any object in motion, average velocity is given by this expression, right? Well, we have the top speed, which is the velocity for this car. We have the displacement for this car. The question we're being asked about the second car is, can it beat the other car? We're talking about time here. So we really need to know how long it takes the first car to get to the bottom of the shaft. So for car 2, we have delta x. We have VI, because that's 0. It's starting from rest. That's 2072 meters. Do we have delta t? We don't, but we do. Because we can figure out how long it's going to take that first car to get down the shaft. Rearranging this to solve for delta t gives you this. Delta t equals delta x divided by the velocity, and I'm just going to put in here the velocity of car 1. So now we have, this is exactly the skill set that you're going to use a lot when we do projectile motion. We have an expression for the time that we have to beat, in essence. And from this point, there are sort of 2 ways to do this problem. So we now have a, VI, an expression for delta t, and we're interested in acceleration. This is what we would like to know. At this point, do we have an equation that ties together delta x, VI, delta t, and a? We do. We have we have delta x equals VI delta t plus 1/2 a delta t squared. Note that nowhere in here do we touch final velocity. We're just simply thinking in terms of time. And your book does some really weird thing where they, anyway. So a couple things happen right off. What's the initial velocity for car 2? 0, which means this whole part of that equation disappears, which makes this much simpler. So we now have delta x equals 1/2 a delta t squared, and we're interested in solving for a. So we now have an equation we can rearrange. So if we rearrange that to solve for a, we get 2 delta x equals a delta t squared. Divide both sides by delta t squared. And we have an expression for acceleration. for the second car. Now, we still need to get this expression for delta t in there. Okay, it's not that hard. So we take 2 delta x, and then here we have delta x over the velocity of car 1, I'm abbreviating that C1, that whole thing squared gives us our acceleration. So 2 times 2072 meters divided by, and I'm going to do brackets here, 2072 meters over, and I did the conversion to meters per second for the velocity of car 1, and it's 1.805 on and on and on times 10 to the first meters per second. That whole quantity squared gives us the acceleration that we need for the first car. So that gives us a raw answer. Hold on. I have a serious error, so somebody might have gotten this right, though I don't think I saw anybody using the equation. Did you get 0.314? Okay, I'm sorry, Jason. I'll give you a gold star on your forehead if you want for the rest of the day. Okay. I just need to go find my gold stars. I might have smiley stickers available. Yeah, that also means he gets a 2 out of 1. So that's better than a gold star or a smiley sticker. Okay, so you get an acceleration of 0.31467 meters per second squared. It's not that big an acceleration. It's not that big an acceleration. And what your book does is prove, what. So they basically need to have an acceleration greater than that by anything. So, that plus 0.5 meters per second squared. And they beat the other car. The other route you can take, the one that I took, was taking this time and adding a second. So in order to beat the other car by 1 second, if I take this whole expression and put a +1 in there, then, so there are 2 routes to take there. You can find the acceleration that gets them there at the same time and then say it has to be greater than this, or you can find the expression for time and add a second, add a half a second. It's probably cleaner and more elegant to find the acceleration necessary to get them there at the same time and then say it's got to be greater than this. Because we don't care by how much they beat them. We only care that they beat them. So it could be a nose. It could be, beat them by a chin hair. Don't care. Better? Well, let's figure out what top speed they get. Here's why this works. This is kind of like biological evolution. 2,072 meters is a heck of a long way. That's a long distance over which to accelerate. So, you're accelerating over a very long period of time. That's the critical piece here. Good job, Jason. Let me look at your paper and I'll rescore you and give you your bonus. Other questions? Dis-ease. But here's the thing. You have to look at what's actually there and what's not. Final velocity is nowhere there. You have to look at what you actually truly know because you have to go back again and again and again to relying on what you truly know. And that's why I gave you a problem like this. I wouldn't give you one like that cold on a test because that wouldn't be fair, but I have no compunction about giving it to you on a FIP and making you go, rah! That's what FIPs are for. So, and I won't say you won't have something challenging like that on the test. But I typically provide some options, you know that. So, okay. Tell you what, we are going to extend the deadline for homework because I want to add something. Because I forgot that there were some problems that are extra challenging problems that I do want to give you. Because I knew that we weren't stretching your brains far enough, and I remembered as I was flipping through my materials, I'm like, oh yeah, we haven't done this. So we got some additional kickers to throw in. So right now you got time to work. For now, let's say homework will be due on Monday. We have a single period on Monday? No, we have a single period on Monday. I am so confused about that this year. Okay, so single period on Monday, homework due then tentatively. That's it. Keep working.